We look now at our first differential equation with a discontinuous forcing term at the end of it. We are going to apply Laplace transforms in order to solve it, since we cannot use undetermined coefficients or variation of parameters. Please be aware that this problem might end up being fairly long, and so if at any time you wish to pause the video and reverse it, it would be a fairly useful exercise to do. I will only be doing a video on example 4, so the next video after this will be the following example, example 5. If you need extra paper, it may help as we go through this problem. What's nice about it is that the Heaviside notation has already been implemented for us, and so we're going to begin first by taking the Laplace transform of both sides of the equation. In so doing, I end up with 2 times the quantity s squared y of s minus sy of 0 minus y prime of 0 plus sys minus y of 0 plus 2 y of s is equal to e to the minus 5t all over s minus e to the minus 20t all over s. If you need to look at a table of Laplace transforms in order for you to verify that this is indeed the Laplace transform of these two functions here, that is perfectly fine. We observe the following. We observe that y of 0 is going to evaluate to 0. Y prime of 0 will evaluate to 0. And so what remains is the characteristic polynomial, 2s squared plus s plus 2 times y of s, and that will equal e to the minus 5t minus e to the minus 20t all over s. Dividing both sides by our characteristic polynomial will give us the following. It will give us ys is equal to e to the minus 5t minus e to the minus 20t all over s times 2s squared plus s plus 2. And no matter how you decide to do this problem, if you decide to split it into 2, it becomes an exercise in doing the same set of partial fractions for both. The e terms right here only indicate that we're going to uncover another set of Heaviside functions. Since our Heaviside functions appear here in the solution, we would anticipate that having the Heaviside function times h of s, as is the case, that if I have the Heaviside function u sub c of t times f of t minus c, that this is what is going to give me e to the minus cs times capital F of s. And so we can sort of split our problem up, taking away the algebraic portion from the exponential portion so that we recover this fs right here. And since the exponential portion is composed of 2 e functions, I'm going to just put those off to the side, knowing that they're going to result in the Heaviside functions appearing in my final solution. And so I'll have e to the minus 5t minus e to the minus 20t times this function right here, which I will call h of s. And our goal right now is to find h of t, since we know that the final solution, or the final function y of t, is going to equal whatever this h of t is, shifted by 5 times u sub 5 of t, plus h of t minus 20 times u sub 20 of t. It will be the same h function that I'm going to employ for both of those, since that is what's going on in here with my two e functions. Using this formula here, I work backwards, and so my goal right now is to find this h. In order to find the h, I set h of s on its own, and so I get h of s is equal to 1 over s times 2s squared plus s plus 2. I can split this now into a over s plus bs plus c all over 2s squared plus s plus 2. And then I need to solve for a and b using partial fractions. I'll go through the partial fractions in this particular case as it may prove to be instructive for some. When multiplying through by the greatest common denominator, I will end up with 1 is equal to a times 2s squared plus s plus 2 plus bs plus c times s. The way that I do this is I focus on specific terms. So I'll start first of all with the s squared terms, then I'll go to what will make an s term, and then what will make a constant term. So for example, in here we see we get a times 2s squared and bs times s, and so we're going to end up with as squared, or 2a plus b, which must add up to 0, since there are no s squared terms on this side of the equal sign. Now let's go to the s terms. I'll find that a times s will give me as, and s times c will give me cs. And so those would be the two terms that I would combine in order to get the s coefficient, but there is no s term on the left, and so the coefficients must sum to 0. What's nice about this is it means that a and c are exactly the same value, except they are opposite signs. And so then lastly, I will try to get my constant term, and the only constant term I get is 2a. And I get that 2a is equal to 1, which means that a is equal to a half. This means also that c is equal to negative a half, and since we have 2a plus b, when I put a in that equation and try to solve it, I get that b is equal to minus 1. This leads then to the following partial fraction decomposition of h of s. H of s is going to be 1/2 all over s plus negative s plus a half all over 2s squared plus s plus 2. It isn't always obvious to us how we have to split these up, but what is clear is that since the denominator below is not factorable, we have to do some sort of completing the square to get it into its form. Once we have completed the square, we'll have a better understanding of how then to transform the function. So let's go ahead and do that. Focus on completing the square for this part of the problem. And when we do that, we will end up with the following. I will go ahead and pull my 1/2 out of both of these terms. And so that when I do that, I get 1 over s. And I'm going to pull out a minus on the second term so that I end up with the following. I end up with so that I end up with s plus a half, and the 1/2 is coming from the denominator. So let me go through that actually before I do this. So that means if I pull a 2 out of the denominator in the second fraction, that will give me s squared plus 1/2 s plus 1. And what's nice about that is I can now pull a 1/2 out of both of these terms so that I end up with 1 over s minus s plus a half all over s squared plus 1/2 s plus 1. At this point, if you need to stop the video so that you can go back and make sure that you understood how the partial fraction decomposition happened, it would be a good time. Generally speaking, when we do completing the square, we don't want a coefficient in front of the quadratic term. So that's why I pulled a 2 out. And then where I got the 1/2 is that I can pull a 1 out of the numerator and a 2 out of the denominator. This 1/2 in the numerator here could certainly be written as 1 over 2s. And so 1/2 comes out of both equivalently. Let's go and do our completing of the square so that I have now h of s is equal to 1/2 times 1 over s minus s plus a half all over s squared plus 1/2 s plus a blank and plus another blank since we have to borrow from the 1. In order to find that blank, I take the middle term divided by 2 and square it. And I get 1 over 16. And so that's what I'm going to put in that place there. But that means that I have to borrow 1/16 from the 1. So what remains is now 15/16 with the 1 over there. Grouping these terms, I end up with 1/2 times 1 over s minus s plus a half all over s plus 1/4 the quantity squared plus, and I'm going to make this the square root of 15 over 4 the quantity squared. We will see why in a minute, but one of the reasons that this is a good idea is because we know that we have a couple Laplace transforms that, that work. One is that if I were to take the inverse Laplace transform of the cosine of AT, that this is going to be s all over s squared plus a squared. And if I take the Laplace transform of the sine of AT, this is going to equal a all over s squared plus a squared. So having this denominator term right here written in helps me to determine how I am going to modify my numerators in each of the cases. Now, the second thing to observe is that we have a shifted Laplace transform right here, where the shift is by 1/4. And so, and the reason that that becomes significant is because whenever we have this shift, we know that it is going to result in an e forming in the t space, so that we would have e to the ct times the inverse Laplace transform of capital F. These seem to be the three that are recurring rather frequently in our experiences right now. So since I have a 1/4 in my parenthesis right here, I need a 1/4 up here in this s to show that there is indeed a shift. And so this will be 1/2 of 1 over s minus, I will go ahead and make this s plus a fourth, but then that means that this 1/2 gets split so that I have a 1/4 again. And so now I have s plus 1/4 squared plus the square root of 15 all over 4, the quantity squared. So given that, I can now split this because linearity helps us in this particular case. I can split this so that I get s plus 1/4 all over s plus 1/4, the quantity squared, plus the square root of 15 over 4, the quantity squared, plus 1/4 all over s plus 1/4, the quantity squared, plus the square root of 15 over 4 squared. You can see you're spending a lot more time finding the inverse Laplace transform than you are actually solving the equation. So we have the following piece of information, though, that the sine, the Laplace transform of the sine is going to be a all over s squared minus plus a squared. And since we already know that there is a shift in the Laplace transform, this sine term right here is also going to have an e when we do the inverse. What needs to happen is that the a needs to appear. And since my a is square root of 15 over 4, I need to put a square root of 15 in the numerator. However, in so doing, I have to end up dividing by this very same term so that I do not modify the problem. And so I'll put the square root of 15 over 4 there, but multiply everything by 1 over the square root of 15 so that I end up with this. We're not worried about the s plus 1/4 because, again, that is going to result in a shift, which gives us e to the ct. And now I have my thing completely split so that I can find the Laplace transform of it. So going term by term, the 1/2, of course, is from linearity, it's not going to matter. The inverse Laplace transform of 1 over s, let's recall that the Laplace transform of t is equal to 1 over s. And so this will end up just being simply 1/2 of t minus the form that we're going to use is the cosine Laplace transform that has been shifted by negative or by c. And so since our c in this case is positive 4, or since positive 4 is in the position of c, we have to make it the opposite sign. And so this is going to be e to the minus 1/4 t times the cosine of, and then what goes in is the a, the square root of 15 over 4 times t. So we have the a term here, and the a appears in here. We have a minus c here, so the opposite of minus c appears up in there. And the same thing is going to hold true with the, and this should be minus as well, with the sine term. And so we get minus the square root of 1 over 15 e to the minus 1/4 t times the sine of the square root of 15 over 4 times t. And that is your solution. Well, that is not your full solution. That's your partial solution. What we just found there is our h of t. And so that is the h of t that we would use in our function. The actual solution, y of t, is precisely the form that we gave earlier with the particular shifts. If you recall, that would be u sub 5 of t times h of t minus 2 plus u sub 20 of t times h, it's not 2, I'm sorry, 5. H of t minus 20. And so this would be the solution of the differential equation.